Hello. I'm gonna present you Skirack, one tool I've been written in order to generate ROP payload. So this is the second talk related to return-oriented programming. Okay, so let's begin. I work in an IT company called Hervé Shower Consultants. We're about 20-30 people. I perform mostly any IT security assessment, mostly highly technical. And we have been one of the first company in France performing a pen test. Myself, I'm Baptiste+Aviat, so I mostly perform pen test and technical audit for this company, and I've been in HSC for 3 years. Okay, so I'm going to talk about little the concept of the return-oriented programming for those of you who don't do daily exploit writing. Then we are going to see how we can construct a ROP payload in practice. And I'm going to explain you what are gadgets and why we need a tool to construct a ROP payload. Then I'm going to introduce you the basics of my tool, so Skirack. And we're going to see in practice how we construct a real payload. And then I'm going to show you a little demonstration of the generated exploit. Little parenthesis, there is a mistake on the when I sent the name of my tool to Sysdream. So for the French people, there is a little play on word with Skirack. This is related to the name of a French radio. I'll let you think about it during the presentation, and I'll be able to explain it to you after. Okay, so what is ROP already? So the buffer overflow in ages began with free exploitation. Okay, we discovered a thing, and there was no protection, so everything was really good for exploit writer. Then comes some protection measures, such as the stack randomization. Okay, so we were not able to push some static offset in order to jump to our payload. So we use opcodes such as jump ESP to jump to the stack. Another bypass has been to use to mark the memory as only writable or only executable. So this way, attackers were not able to push shellcode on the stack and to jump to it and execute it. And this has been bypassed by the return into libc method. And then the ASLR, which allow to randomize some libraries and some programs in order to have a non-static address. So we could even use such opcodes in libraries, since we don't know their address. So the return-oriented programming, the return into libc, it allows you to call external library functions, even to chain calls, but it is often difficult because in this way you can only push static arguments on the stack. You are not able to compute dynamically arguments, of course. So the ROP allows you to use arbitrary instruction to compute exactly the argument of the function as you want. So this is a great advantage on return into libc call. So the thing you have to understand to get the ROP is the ret instruction. Okay, this is a really simple instruction you can find at almost the end of any function in any program. Ret does pop EIP. Okay, EIP is the pointer of the instruction that are currently executed by your processor. And if you do a ret, it will take the top of your stack and push it into EIP. Okay, so ret means that we take the first value on the stack, we remove it, we push it into EIP, and we're good to go. Okay, so the address on your stack will be executed after if you run a ret. instruction. So before we smash EIP, usually we have ESP pointing somewhere. We have just below the saved EIP, and currently EIP is pointing to a vulnerable function and the ret. Okay, so that is just before we gain execution. Next step, the ret is executed. As I said previously, the top of the stack is gone into EIP, and if, like it was the case, EIP is now pointing to an instruction which is followed by a ret, you can see that the next instruction executed will indeed be the ret, and so, same schema as before, the address in the top of the stack will go into EIP. Okay, so indeed, this way, by writing such address on the stack, if all the address point to instruction followed by a ret, we will be able to execute as many instructions as we want, or more precisely, as many instructions as we have room for on the stack. Okay, so the second gadget returns, and here the second gadget has returned. So after we don't know where we go. Okay, so what is the goal of a ROP payload? If you use only a return into libc, typically you will execute things such as running a shell or adding a user. But with return-oriented programming, you can perform more and more things, such as pushing arbitrary shellcode on the stack. So how do we do that? We prepare the execution of a traditional payload. So we allocate some executable memory, or we disable NX, or we grant executable permission to some memory mapping. We can resolve address. There is many things that can be done. Then we copy or we jump to the payload. So any payload. It could be a reverse shell, but it could also be Meterpreter, for instance. Okay, so what do we need to build a ROP payload? We need a program. We take a DLL or a library of this program. And the first time you need to build a ROP payload, you think about it and you say, okay, I'm gonna disassemble the thing, and I'm gonna grab for ret instructions. Okay, this way, this might be feasible, but it's quite difficult. If you need to write some extensive thing, you will take a lot of time. So there is some tools. Okay, there is ROP.me, which is 32 bits Linux only. There is some things in the immunity debugger, such as find gadgets, which builds a flat gadget.txt file, which is quite difficult to parse, and limited to Windows 32 bits application. There is the dead PV find.addr, and of course there is Mona. Thanks to Peter, or thanks, not sure, because I spent a terrible night because of him, but. No. Okay, Mona is really a big deal. But seriously, you're all working in security-related domain, I guess, or if you're here, that's because you really like security, I guess. How among you does security for money? Come on, don't be afraid. Okay. Who among you does security for fun? Okay, if you make security for fun, you don't want a tool that does all the job for yourself. Okay, come on, it sucks. Okay, so I can say Skirack, the fun of Skirack is really higher than the fun from Mona. Okay, because it is a lot more work to build a payload with Skirack than with Mona. I'm sorry for that. But that's what it is. No, seriously, Mona is really a big deal. But there is different things you can do with my tool, and I'm gonna show you. So, do we really need a tool? See, if we take a library, we can, for instance, here the libcrypto, and we look for the ret instructions in this library. You can find about 6,000 ret instructions in it. Okay. 6,000 ret instruction. Does it mean 6,000 gadgets? Yeah, no, maybe, I don't know. Of course, no. Okay, if we disassemble a few instructions before a ret, okay, so here 64C, we can see this is a move R14 into RSP, the contrary, move RSP into R14. 64D, so just an instruction after. This is a different instruction, okay? This is move RSP into ESI. 2 octet before, we get again another instruction, okay? So since x86 has different opcode sizes, if you disassemble starting from one address, you may find some instruction, and if you go 1 byte, 2 bytes, 3 bytes later, you can find different instructions, okay? So here, one ret, 11 gadgets, okay? So we are limited in this graph to 5 instruction back. There is an arbitrary, you can go back as much instruction as you want disassemble, but here 11 gadgets are usable with one ret, okay? There is on your right the GL26, which which is not useful, so I didn't count it. Okay, so we need a tool to parse and to find some gadgets. In this library, there was, in average, 12.25 instructions per ret, with disassembly of 5 instruction depth, okay? Which means 5 instruction depth that if I take a ret, I will stop in this tree after 5 instructions, okay? But you can go as far as you want. So it's getting hard to grep, and we do need a tool. So I've been writing Skirack. This is based on MIT-ISM. MIT-ISM, I don't know how English guys say it, but it's written, so you should understand it. So it allows to disassemble many kind of binaries. Linux ELF files, Windows PE files, and Mac OS macro FAT files. I handle 2 CPUs, x86 and x86 64-bit, and no PowerPC, of course. So it's quite easy to import new architectures in this tool as long as they are supported by MIT-ISM. There is only a few methods you need to override in order to get it to work with different architectures. For instance, the base address of a section, the list of the section, and stuff like that. So okay, so it also uses Intel syntax for the representation, for the graphical representation. Graphical, textual representation of instructions. So how do we build a gadget database? There is an instruction which is skybuild. So you give as an instruction the name of the library you want to build the gadgets for. So all this library will be parsed, and we store the result into a SQLite database. Okay. Once this is generated, you have to think about your exploit, so how you will construct it, what you will do. For this, I can't help you. This is your job, and this is why Skirack is fun, I recall. Then you can build your exploit by looking for instructions you need. So there is an elaborated search function in Skirack. The simple form is to use, for instance, a row pattern, such as move EX. This will list all the gadgets which contains move EX, but in a smart way. I will tell you more about that later. Then you have found all the instructions you need. You can put them in a file. Okay, so you build your exploit.txt file. This is a human-readable file, which only contains at the beginning the address of your opcodes and then the list of the opcodes. And you can put many different things in it, just to help the generating of exploit, but more about it later. And once you have your file built, you can generate your exploit. So there is SkyGenerate, which will turn the human-readable exploit.txt into a raw binary file. Once it's done, you can get a beer. You should be happy. Okay, so some use cases of ROP payload building. Okay, here we have run rate. How many gadgets do we have? Come on, count. I'll wait. 6? Okay, 6, that's the only answer? Come on. 1, 2, 3, 4, 5, 6, 7, 8, 9. 12? No? Okay, 6, 12. Only 2, of course. You have a jump here. So you won't be able to execute the instruction before you will jump to somewhere to the unknown. Okay? Not interesting. There is only 2 instructions you can use. Okay, so if a tool gives you all this kind of gadget, this cannot be used. So in Skirack, you can keep only the executable branches. Okay, there is an option which is preserve EIP, which will cut off the branches which are not executable in the gadget graph. Okay? So imagine you're searching for another gadget and you need to add 8 to array X. Okay? Maybe to point it to the next address. So you have found the instruction of your dreams in a gadget, which does exactly that, add 8 to array X. But the gadget does not fit. Why? Because the add array X is followed by an instruction which makes array X to 0. Okay? So it's not usable. So you can tell Skirack to skip the non-executable gadgets. So if you use the option preserve target, you will be able to skip all of those registers that modify the register you're looking for. Okay, so here we are looking for an instruction which appears on EAX, and if we use preserve target, all the branches that modify EAX will be cut and won't be shown to you. And you can skip also gadgets that only modify a specific register if you really need it for your previous gadgets or for some reason, I don't know. And you can just use preserve and an arbitrary register. Okay, so if you need to preserve the ESI register, you may find it difficult to find such instructions, such as move ESI into EX or rechange EX and ESI, depending on the binary file you are passing. So you need the following: push ESI, pop reg. Okay. This is sequence of instruction which is quite difficult to search for if you're in a flat gadget file. So you can combine the instruction you need to search by pushing multiple times the -A option. Okay, so here -A pop ESI, -A push will return all the gadgets which contain the push pop ESI instruction and the push instruction. Then you can search for specific registers. For instance, if you need to add a specific value to arrays, or if you have to perform operations between RBX and RCX. And when you build the ROP gadgets, you will quickly realize that you often need to do a lot of work with registers because you don't know often where memory pointers are to, if it is valid address or no. So the most reliable thing is to use those registers. In addition, these registers are really the most common in the instructions you'll find. So it is really, really useful to be able to filter them. So if you want to search for the move instruction, and you search for the destination with the option regs, it will show you all the move instruction which appears on registers. Okay, so if you're on a 32-bit processor, EX, EBX, ECX, EDX, and that's it. You can also search for a specific register with -D array X. Okay, Skirack also allows you to convert payloads. So there is a SkyConvert tool which helps you to convert a payload written for a specific library to a payload for another library. In this way, it's really easy to convert an exploit. For instance, if you use two libraries, you've been written an exploit for libSSL 098b, you will find that your exploit does not work longer on OpenSSL 098c, because there is some differences in the binary, and so the gadget addresses are completely different. So if you're lucky, you may also port your exploit to a completely different lib, because some instructions are somehow common and can be found in different libs. But it's not as flexible as Mona, and you will need to build your payload in a specific way to get this to work. Okay. So the use for this tool is a Sky Convert, and you take as an argument your exploit the txt file. The two database built by Skirack, which contain the gadgets, and the output will be the new exploit.txt file. So once you have built your payload, you generate indeed the payload. So this is Sky generate, you take an argument, the exploit.txt file, and you construct a raw binary file. So this command is just enough to build the exploits. So if you are exploiting local software, Sky generate allows you to pass an offset, which may be useful to brute force local exploit or remote exploit, which can be triggered multiple times. And this way, you will be able to brute force some offset. For instance, if you have a Windows SLR, you may find it useful. So another good point is that you can script it easily. So it is Ruby. This example is in IRB. It's the interactive Ruby shell. For instance, here I just launched Sky IRB. I require one file from Skirack, and I can load a database into the IRB. And then I can list one specific gadget. I can search for different gadgets and stuff like that. Everything is easily callable from the Ruby interpreter or from any of your scripts. Okay, so next step is the payload generation. So here we will be really building the payload. So one of the typical ROP scheme you may use is, for instance, to use a combination of virtual alloc, memcopy, and jump EAX. This will allow you to allocate some specific memory and to copy your shellcode in it and to jump to it. How can we do that? So we need to prepare the stack with the arguments of the virtual alloc function. So it takes destination, size, allocation type, and the protection of the memory you're trying to allocate. Next step is to craft the memcopy arguments, because memcopy needs the destination buffer and the source buffer. And when we are writing the exploit, we are not aware of any of these arguments. Of course, you need the size, and at the bottom of the stack, we will put the shellcode. So the difficulty here is the arguments from memcopy. So the following arguments are unknown when you write the payload. You don't know the destination buffer, and you don't know the source buffer. Hence, we need to find the memory, where the memory has been allocated by virtual alloc. So this is virtual alloc return value. This is the same thing for malloc. We need to find the shellcode address, which we know is at the bottom of the stack. Since we are writing the payload, we know the distance of the payload from ESP. Okay, this is something we can decide by putting in lower on the stack or upper on the stack. We decide. And finally, we need to write these computed instructions, these computed values, on specific places on the stack. Okay, why specific places? Because of course we need to write it exactly here and here. If we write it lower, we will smash the size. Upper, we will smash the return value of memcopy. So we need to be really precise in this case. So one assumption for this demo is that the stack grows up, that we don't care about ASLR or that we are performing brute force, and that we control EIP, okay? We don't care about stack protection, SCHOP. We imagine that you already gain EIP, okay? And the payload can contain null bytes, which is a requirement in 64-bit ROP exploitation because memory addresses are full of null bytes. Okay, so we prepare the virtual alloc call. That's the easy part, since all of its arguments are constants, okay? So we prepare the arguments, okay, no problem. What happens when virtual alloc will returns? It will put ESP at this place. EIP will receive the saved address, okay, the saved address which is indicated here. Next step, if we put a ret address in the saved address, it will just pop the top of your stack into EIP, and so we will be able to execute the address we have found where the arrow is pointing here. So we need to find a ret. That's really easy. You just search for a ret. Here, we found a ret. Okay, good. We need then to craft the memcopy arguments. So we need to save EAX. Why? Because EAX is the return value from virtual alloc, and then it contains the memory which has been allocated. Okay? So we need to save EAX. We need to compute the memory arguments address. Okay? So this is this address, because the arguments we need to write are pointed to by this address. We need to copy the saved EAX to this address. Then we need to increment this address in order to get it to point to the second argument. Then we need to compute the shellcode address, which is the address of this part. And we need to write the source address, the address of the shellcode into arg+4, okay? Then we will be able to call memcopy. And if we use a specific instruction here, we will be able to jump to our shellcode. Okay, so how do we craft the memcopy arguments? To save EAX, it's easy. You can just use the hsearch instruction with which operates on which can operate on EAX. So with this simple search command, you will find this instruction. Okay, so we put in our ROP chain this instruction, this address, I mean. Then we need to compute the memcopy arguments. What is the address of the shellcode? This is an incremented value of ESP. Okay, this is ESP minus all the ROP exploit we are building. Okay, if you recall, we are building this ROP chain, and the shellcode is here. So we need ESP plus many bytes in order to get here. So we can search for interesting add variables, and we will mostly find add on which occurs on EAX. Okay, so that's good. We will use this this value, but for this we need to push ESP into EAX. Okay, so we need to copy ESP into EAX. We won't find no move ESP into EAX, so we will have to use the stack. Okay, so if we search for instruction combining push and pop, we will find this one, so which performs push ESP, pop ESI. What does it do? It just transfers the content of ESP into ESI. Then, if we look for move specific move instruction, we will find an instruction which moves ESI into EAX. So in this way, we have right now ESP into EAX. Of course, if we can't write directly this gadget instruction, we need to put some junk, some padding between the instructions, since there is some parasite pop which will decrease the stack. In fact, increase the ESP value. Okay, so once we have done that, we can write all of it in our shellcode. And if you recall, at this line, we have a backup of EAX into the last line of the ROP payload. I mean, we have a backup of EAX into EDX. Okay, and we have in EAX the value of ESP incremented of 40 bytes. Okay, so right now we need to write to the address pointed to by EAX. So we search for simple instruction which use the pointer into EAX. So we found just the one we need. Since EDX holds our EAX backup, this is enough to craft the memcopy first argument. Okay, so let's add this line to our ROP shellcode, to ROP payload. And then we need to add for to EAX to point it to the next memcopy argument. But we don't have no add EDX4 instruction. But if we look for instructions that operate on EAX, we will find an instruction which does to inc EAX. Okay, so if we combine this gadget twice, we will indeed add 4 to EAX. Okay, so we are almost done. We have incremented save DSP to get it to point to our shellcode base DDR. And then we pop enough bytes from the stack to get to the memcopy address. The memcopy return value should be our copied shellcode address. And luckily, just like it's designed for ROP building, memcopy returns the address of the written area. Okay, so you just need to jump to EAX after you've been executing memcopy, and you will jump to your shellcode. Okay, so there is another tool in Skirack, which was just 3 lines long writing after I've been writing the other, so I'll write it. And it allows you to search for a specific instruction. In fact, it takes the instruction you give it, it just compiles it, and it looks into the binaries for this instruction. It's useful, for instance, if you search syscalls, because I'm not aware of any syscall search instruction in MITISM, or you already need to compute the opcode of syscalls. Anyway, it's just a bit faster. That's it. And so we find the offset of a jump EX in our library. And then we can add it to our payload. So the full exploit can be written in a file. In order for the file to be handled by SkyGenerate, I just add a few syntax things. If you have I don't know the English word for this character. If you have a point d'exclamation, I'm sorry, you can put Ruby code just after it, and it will be executed. Okay. For instance, if it returns a string, the string will be included in the shellcode, and then you can put all of your instruction, and so give this file to SkyGenerate. And there is also a command, of course, in order to have clear exploit files. So this will allow to write comprehensible and portable exploit files, which are often more clear than some ROP exploits you can find on the internet, which are quite difficult to understand. So you can generate the payload, SkyGenerate your exploit, you pipe the output in some binary file, and you can run it. So I'm gonna show you a little demonstration for this. Okay. Okay, just keep this way. So here we are in HolidayBG, and we are just at the ret instruction of the vulnerable function. Okay, so you can recall the exploitation we've been writing. The first thing will be to jump to virtual alloc. Okay, so the next instruction will be a jump into the next instruction executed will be virtual alloc. Okay, so here we are in virtual alloc. We need to put a breakpoint at the end of virtual alloc because we don't care about the internals. So here we are just before virtual alloc returns. Okay, remember what I did? We just put a ret for the instruction executed after the return of virtual alloc. So the ret will be executed. Up, here it comes, and we can see we have indeed crafted the stack with virtual alloc arguments. Okay, so the return. Here we can see we have exchange EX, EDX, which is our backup for EX. We'll return. Next gadget, this is our way to save or to transfer ESP into EX. So remember, we push it on the stack. We pop it into ESI. That's it. We return. Then we move ESI into EX. There is a pop, so you can see on the stack the padding. We return. Okay, next instruction, we add 40 to EX. We return. We can thread. We move EDX into the word pointed to by EX. Okay. We ink EX twice, 4 times in order to get it to point to the next address. And the end of the execution is the crafting of the second argument of copy, which I didn't detailed in my slides. Okay, so this way we've been able to follow the execution of the ROP payload. This is something quite nice to see the following execution of the gadgets in a debugger. Okay, so here we're done. I'm going to show you another video which will only run the exploit in real time, not in a debugger. Okay, so on the left we have a Linux machine with Metasploit. On the right we have a Windows machine, and all I've been doing is that I run the exploit, and so here we have been able to indeed use a Meterpreter into Metasploit. Okay, so we indeed gain execution with it. Okay, so that's it for this tool. If you have any question, I'm available. And this tool will be made available. I hope it would be today, but it should be tomorrow, since the guys handling the website at Rock seems to have a lot of work today. So maybe beginning of the next week, but it is pushed, and it does not depend on me. Will be available very soon. Okay.
You said you can port some ROP payload from one library to another one. Do you have a way to choose a ROP payload which is compatible with 2 different versions of the same library, or is there a way to script this kind of research?
Indeed, to convert the payload, you need to generate the database of the gadget for the second library. Okay, so if you have one ROP payload, it will only look for the equivalent instructions in the second library, so there is no difficulty to do that. But there is no need for scripting, since it's only two commands to. Well, of course you may script it, but it's only two commands you need to generate the payload for a second library. Did I answer to your question? Okay. Any other question? Can see nothing with the slides. Okay, well, thank you very much.